Welcome, everyone. We're going to redo a talk we did at GDC 2024 right now about Sentis, our neural engine. And we'll be talking about driving better gameplay experiences on end-user devices with artificial intelligence. My name is Bill Cullen. I'm a product manager working on Sentis, our neural engine. I also have Alex with me. He's our lead staff engineer working on Sentis. So here's the key question. Why would you want to bring an artificial intelligence model into your game? And I'm not talking about game creation in the Unity editor. I'm talking about in runtime, right in your game. So here's the reasons. It's all the use cases for AI models. So we're talking about things like speech to text, building unscripted NPCs, doing text to speech, depth estimation, so many new things that are either just really hard with deterministic code or frankly impossible. Last year at Unite, we showed some really cool use cases of all you developers creating some amazing things with Sentis. We showed enemy behavior in the Bone Lab app. We showed breath detection with Trip Meditation VR. We showed unscripted NPCs with a Unity demo. We also showed some really amazing indie developers. We showed muscle activation and neural rendering. Today, we're going to take it much further. We're going to show 3 new demos that show off 3 brand new use cases that people are using Sentis for. We're going to show hand gesture detection, board game opponent, and story generation. Some really, really cool stuff. So the big idea is we think Sentis, the neural engine, is a really transformative component in the engine stack. And it's right alongside things like the physics engine, animation, sound, all the things that you know and love in Unity. So there's something a little bit unique, though, about running neural networks in Sentis. It's basically a really nice problem-solving buddy. So the input in this case would be some WAV file chunks of audio. The neural network would process those chunks. And in this case, we call that inference, which is just a special name for running the program. And the outputs would be some text strings of what the audio is. And so the neural network is quite good at basically making these inferences or sophisticated guesses. Okay, so this is awesome. We have this new problem-solving buddy in the Unity engine. But of course, it's not quite that simple. There are some key problems we need to overcome to kind of merge this AI world with the game development world at the level of the runtime. So the first problem is that most neural networks are written in Python. The issue is that Python does not run natively in Unity. You can get it to run if you run a local Python server, but that's pretty cumbersome and you're kind of limited to which platforms you can deploy to. It's kind of relegated to desktop. So to overcome this, we convert the Python to our intermediary representation. Those of you familiar with Sentis might be familiar with our .sentis file, and that's what that is. So the next issue to overcome is really having a fast frame rate. This is the real reason you're running a neural network locally on the end user device. So to get a fast frame rate, obviously we've already removed the internet connection from the equation for running the inference, but we also have to do some interesting optimizations for the model, which we handle automatically in Sentis. And the last thing is easy deployment. The reason you're using Unity in the first place is for probably our build once and deploy everywhere capabilities. And that's exactly the same with Sentis. We have a single API that automatically integrates with all of the Unity runtime platforms. So you integrate the model once, and you can trust that it's going to work on all the runtime environments. So at the end of the day with Sentis, what we're offering is really the default AI inference tool in Unity 6. It's really fast. It's fully free for unlimited use. And it's private because you're not sending any data to the cloud. Of course, you can do an integration once with the Sentis API and deploy your app just like you normally would to all Unity runtime platforms. And what's really nice is that you can use all the same Unity systems you're already using, like the profiler or the job systems. And by the way, it's getting faster all the time. Okay, so let's do a quick run through of how to implement Sentis in your game. Step 1 is to get an AI model or train it yourself. You can go to a marketplace like Hugging Face, TensorFlow, Keras. These are some really popular places to get models on the web. Step 2 is to convert your model to the Onyx file format and import into Unity editor. Assuming you have the Sentis package installed, all you do is drop that Onyx file into the project assets folder. Next step is where the real work begins. You need to integrate those network inputs and outputs, we call them tensors, to your C# game code. And here is where you'll probably need to do some optimization of the network and your game to get it to work really, really well. Step 4 is to deploy your game or runtime app just like you normally do today. So let's take a look at the journey that we're on with Sentis. Last year, we launched a private beta back in June, and then we scaled up to a public beta with a lot more users. Then at Unite in November, we showed some amazing demos of what you guys have been creating. Today, we continue our pre-release cycle of the package, and it's in a really stable and mature state. And so we're really hoping that you can start integrating it into your games in anticipation of the full production release with Unity 6 near the end of 2024. Okay, now that we understand how Sentis can be used, let's take a look at some recent enhancements we've done to the system. So let's take a look at the first part of the process. We've heard some feedback that identifying the right model and getting into Unity can have some friction points. Let's take a look at Hugging Face. This is the biggest model repository out there. It's got over 500,000 models. So where do you start? Well, they've got these nice tags. This one is for audio to text. But if I filter by that, I still see 15,000 models. I don't have time to look through 15,000 models. So we worked with Hugging Face to add this really nice Unity Sentis tag. And this repo here is the Whisper Tiny model that our team has validated works really well in Unity. And we've even pre-converted it to the .sentis format. So there's no Onyx file conversion needed. So you can go here, download the model, and drop it right into the Unity editor, and you can pretty much guarantee that it works. And we've done this with some other models too. You'll notice here that I've deselected the speech-to-text filter, and we've got about 20 models on here that we're now offering. And we plan to offer quite a few more of these over the coming months. So look for more. Let's take a look at the Learn section of Hugging Face. So they built some really nice courses here to onboard you to machine learning. This brand new one called ML for Games features a really, really nice sample demo to get you started. So if you click on the first unit, you'll notice that this is about building this fun robot called Jammo, who can take some input to a sentence similarity model, which takes a string and identifies how close it is to the game lore of the game. So they have really nice visuals here, code samples, and it goes into really, really great detail, especially if you've never gotten started, especially if you've done anything with machine learning. They've also taken it to the level of being able to export and host a WebGL Unity build, which is really, really nice. They have this infrastructure called Hugging Face Spaces that allows you to host that web app and share with your friends. So that's quite convenient. And there's several new chapters coming in the ML Games course, so watch out for those. All right, I'm going to pass it off to Alex to talk about some more enhancements.
Thanks a lot, Bill. That was really nice. As Bill mentioned, we're looking into ways to make it easier for you to find a model and bring it into Unity. So right now, we know there's a little bit of friction because you need to go from PyTorch to Onyx and then import that into the Unity editor. But wouldn't it be nice if you would be able to export directly from PyTorch to something that is Unity compatible? So that's what we're trying to do, and we've been trying out this new library called Executorch. And what that library allows you to do is do a direct export from PyTorch to a .sentis file, and then just drag that into Unity editor, and it'll run natively. So that's what we've been trying to do. It works pretty well. There's a few things to iron out. Executorch isn't all fully out yet. But we're really excited about this, and it's really promising. All right, so we've looked at we're making your life easier to get a model that is already pre-trained and put into Unity. Now let's take a look at what we've done on the side of integrating and making sure your models work efficiently. So the first one is quantization. So quantization is just a fancy word used in the machine learning community to mean compression. So you're all aware of how to compress a file, of like you zip the file, the size on disk is lower. For images, you do JPEG, the memory size is lower. So with model, you can actually do the same thing and compress the weights into a into a compressed format that uses less disk on space. So for example, if your weight is in 32-bit float precision, you can quantize it to use half the range, which we call FP16, or you can be a little bit more fancy and quantize it into int8. So this is really promising, and we've been seeing around 75% model savings with int8 quantization. So that's really useful if you want to ship your mobile on on your phone, for example, where the app size is really an issue. Of course, there's a few gotchas, right? Memory savings can vary. Some models have better savings than others. Quality is all dependent on the model. So for language models, for example, the quality is really good, even though you quantize it. But for some models, the quality might not be there. Performance, it's not there yet, but we're gonna add that in the future. So here we really scratch the surface, and our friends at ARM have actually a talk where they dive really deep into this subject, and they analyze the memory saving, the performance wins, and the quality between the different quantization modes. So here's a sneak peek of what they're going to be showing. This is an example of the Midas depth estimation model that we showed at Unite. So you can see on the left, you've got the original weights, FP32, and on the right, we've got the quantized one. So you can see FP16 is really, really close to the FP32 one. And in 8, you see some degradation, but the quality is still there. So I definitely recommend you going to that talk and learning more about quantization and how to use it and making sure that it's appropriate for your use case. All right, so another part that we've improved is our memory allocation. We've heard a lot of feedback that our main thread scheduling cost was way too high. And the reason for that was that our memory allocation was really inefficient and didn't scale with the number of layers. So we've gone ahead and re-architectured the whole system and made it way more efficient. So right now we're seeing ×2 performance gain, so that's really encouraging. And also we took the opportunity to really clear out any memory leaks in garbage collection. All right, so another part of feedback that we've got a lot is a lot of you are trying to run image detection models, and a lot of these models use this special layer called non-max suppression to filter out any adjacent bounding boxes. So we didn't think it was that useful, but actually it is. So our implementation was notoriously slow and really inefficient. So we took the time and really thought about how to optimize the kernel, and we've achieved it. And now you can get really fast, mobile-friendly performance for non-max suppression, which enables you to run any sort of image detection models natively more efficiently. So what we're going to do is we're going to show you that in a live demo coming up.
Thanks, Alex. I'm really excited to introduce 3 demos we're going to show today. The first is gesture detection. The second is a board game opponent. And the third is story generation. So for the first demo, we have Plinio Needs a Hand. This is from a small studio in Brazil called Sea Fortress, headed up by Gabriel Henrique. So the vision for the game is to build something really fun and unique. And the idea is to use hand gestures instead of a controller or touchscreen for the main interactions. In the words of Gabriel, we want to show you don't need joysticks for games because you have 2 hands. So in this game, Plinio is this really delightful, limbless slime blob, and you need to guide him along the levels. So let's take a look at the problems you need to solve to build this game. So of course, it needs to be fun. He doesn't want to use controllers. And so you need some way to detect gestures in the game with your hands. Now, of course, we've all played some gesture-based games in the past, things like Xbox Connect, the dance pad on DDR, but these all have one thing in common. They required some special hardware or sensors to use. It wouldn't be really nice to be able to do this without special hardware or special API integrations that are different per platform. So that's the idea. Can we get some really reliable hand tracking with just the native camera that's shipped on every device that's out there? And then the last problem to solve is having a high frame rate on really varied devices. They want to support both PC on Windows and Mac, mobile, and maybe some other platforms in the future. So let's take a look at the demo, and then we'll dive into how it works. Okay, so here's the game. You can see we're able to move our hands around, and the game nicely detects their location in the scene. So we start the game by grabbing the go call to action, and Plinio starts moving, and we just need to drag him up to move the bricks so he doesn't fall into the hole. All right, Cleo, we're gonna nudge you along to the end of the first level. All right, beat the first level. Second one gets quite a bit more complex. So we need to grab the sword out of our backpack and grab the sword, and then I'm gonna go kill the floating ghost. Okay, and now let's grab a brick and fill that gap, just like in the first level. And the next is a really cool gesture where there's a number 2 shaped hole in the brick wall, and you have to make a number 2 with your hand, and Plinio deforms to a number 2, and then you can ride that brick across to the other side. Nice. And that 2 also made the door disappear and open, so you can nudge him to the end of the level. So nice. We beat level number 2. Okay, third and final level for this game slice demo. So it's kind of an Angry Birds style interaction. So Plinio is going to eventually get stuck into the slingshot. And then you've got to pull it back and send him safely through the thorny vines to kill the boss. Oh, very nice. And he's going to fly, and then kill the boss. Really nice. And then I'll make it safely to his icy heaven, or whatever this place is called. Wow, that was an awesome demo. Thanks, Gabrielle. So let's take a look at the solution. How did he get this to work? So the first part of the solution is you need the camera frames to detect your hands. So here he's using the Google Media Pipe suite of models, and the first one is called Blaze Palm. So Blaze Palm can detect your hands in the field of view and draw some dynamic bounding boxes and track them through the scene. So the model works pretty well, but unfortunately it's not really temporally consistent. So you need some post-processing to make it more stable and reliable. So this is where the non-max suppression calculation that Alex just mentioned can help out a lot. So this NMS calculation can really help deduplicate bounding boxes and kind of clean up the messy overlapping boxes and get a really nice clean result for the hands in the scene. And as Alex mentioned, this used to be really inefficient and it kind of slowed down the model and performance, but now it's quite fast. So now that you have the hands, the next thing to do is you need to detect left and right in the hands as well as all the finger joints. So this is a second model that's chained under the results. That's called Blaze Hand. That's also from the Google Media Pipe collection. So once you have all the finger joints, now you can simply write some custom heuristics using the joint indexes for all the different gestures that you want to detect. Now, when the team first implemented these models, they were actually using a local Python server instead of Sentis. And we checked out the original demo and we knew that Sentis was going to be a much better solution. After the team migrated from the old solution to Sentis, they saw some really, really nice improvements. So the first is on performance. The inference is running about 5x faster. So it's leading to a much higher frame rate. And because of that, the gestures are a lot more reliable in the game, which is much better user experience. And lastly, now they're not relegated to just desktop platforms with the local Python server. They can run to mobile or other platforms in the future. So let's take a look at performance of this game. So the 2 Google models add up to just 15 megabytes. So there's no issue shipping that in the runtime app. The inference is running at just under 7 milliseconds, which is really fast. And they're able to achieve 150 FPS, significantly higher than their original 90 FPS target. So we're really happy that they could make the conversion from the Python server to Sentis and get the performance working really nice. So Plinio is out on Steam now, and you can go play a game slice of the game. They're working on the game through the end of this year and doing some fundraising on Kickstarter if you want to support them. Between now and then, they'll be improving the performance even more and looking to expand to more platforms. All right, now let's hand it over to Alex to do the other 2 demos.
Okay, so for this next demo, we're going to show you a little side project that our team has been working on. So we all know that Google used an AI model to beat human players at Go. So we wanted to take this and see if it could generalize to any type of board game. So that's what we did. We took the model. We didn't take the one from DeepMind, but we took a similar one from Stanford, and we trained the model. So the model plays against itself. In this case, we train it for Tello. So it plays against itself many, many times. And once it's done training, the model is able to understand the game state and figure out who's currently winning. It's also able to rank the possible moves by the probability of each being a likely chance to win. So once we have that, we have a really good way to analyze a scene and figure out who's currently winning. So now that we have a model who's able to understand the scene and predict who's likely to win, tweaking the AI difficulty and making it fun is now much easier. So in our case, for the easy AI, we just pick randomly the bottom tier, the bottom tranches of moves who are likely to win. But you could also imagine, for example, when the player is winning, you see that the players are winning many turns, one after the other. Well, you could make the AI more difficult and kind of like punish them for the end. Or if you know the player is about to win, you make the AI more likely to pick a bad move. That's really fun, and that allows you to tune the gameplay to what you're trying to make your game fun. All right, so you can see here it's a game of Othello. We're playing against the AI opponent, and we play one after the other, and we're showing the probabilities of the moves which are likely to win with this little particle effect to visualize which are the best move. So you can see the AI sometimes picks the best move, but randomly will pick some bad move to kind of make the player's life a bit interesting. The also cool thing is, since we know who's currently winning and the board state, we can have some nice quotes depending on the gameplay. So if the player is consistently winning, the AI will say a quote that they're losing and you're too good. On the other hand, if the AI starts winning, we say, aha, I flipped the table, I'm winning now, get better. So we can really spice the gameplay up. So how does it work? Is, as mentioned, the model takes in the board state. So in this case, it's a grid. 0 meanings there's no piece on the board. 1 is the player's piece, and -1 is the opponent's piece. The model takes that as input and then outputs a probability map for every single possible moves. And that probability map is the probability that if you were to play this move, how likely you were to win the actual game. The model also gives us a temperature of who's currently winning. And we use those two information to inject them back into the gameplay. So of course, the AI picks the best moves and play, but we also showcase the probability with this nice particle effects. And the game state is used by us to spawn some quotes and kind of taunts for the player. So it's all pretty fun, and we actually showed it at Unite, and people were really excited. But the number one feedback that we got is, okay, this is cool, but how do I apply this to my tactical RPG? I have a Hearthstone game, a card game. How do I apply it? How can I use this for my own custom game? So we took a step in that direction, and we did actually that. So we took we took Othello and we added these magical rules, like kind of spice up the game and add some cool, nice effects. So we've got four spells that the player can take. First is the rotation spell that will rotate every piece around the symbol. The next one is a free spell that just skips your turn. It's kind of a useless turn to skip. It might be useful if you want to not do an action this turn. The other one is a destruction spell. So if you activate this piece, it will destroy all the other pieces around it. And the last one is a flip spell, which will flip all the colors around. So if it was a red piece, it will become a black and vice versa. So we added this move and we retrained the model. It took about 3 days. And now the model is able to play this game. Of course, the rules we added, maybe the gameplay is not that fun, but the model was able to generalize and play the game. So the performance on PC, the model is around 60 megabytes. So that's really small and you can ship it for no problems. Inference on the CPU is 4 milliseconds. So that's really not an issue. So yeah, we're hoping you can take that prototype and extend it for your own board game and generalize to the games that you might be excited to try out. All right, so let's dive into the next demo. So at Unite and at SIGGRAPH last year, we showcased a few demos that uses language models to enhance gameplay and drive NPC interaction. So these demos were really excited, but however, they ran on really beefy machines and were not really practical. So for this next demo, what we did is we took roughly the same experience and tried to see if we could ship that on a really smaller budget on a on the smaller production scale, and on commodity hardware. So in this case, it's not really an unscripted dialogue. We have a storyteller which needs inspiration for their next story. And the player will go around in the world interacting with a few different items that will generate a prompt for a language model to generate a story based on the actions. All right, so now I'm in Unity. So I'm going to press play and then go into the game. And the lizard wizard here is going to tell our hero to go and interact with a few objects in the scene. And this will help inspire them to write a story about what happened.
Good morning, Alice. I am the lizard wizard. Can you help inspire my next story by interacting with 3 items in the world?
All right, so you saw the lizard wizard here is kind of in a rut and want the player to go and do some heroic deeds. And this will inspire the story wizard to write a story about what happened. So I'm going to go around and interact with a few of the objects around. So let's start with this cow.
You meet Daisy, the cow. She gives you a pail of milk.
All right, so I've met Daisy. So first now you notice the text-to-speech was running to generate the voice of the story lizard wizard. And as you saw, while the voice was speaking, this frame rate didn't move. We were doing the computation of the text-to-speech. And everything is smooth and no lag.
You meet a creature made of stone. He stamps his feet.
Right, I've interacted with this rock. Now I've got to choose between this duck or the crystal. I think I'll go with the crystal.
You have found a magic crystal. I, the lizard wizard, have finished writing. Come here and I'll tell you your story.
All right, so the lizard wizard has finished writing the story and is inspired. So now I can go back to see him and get my story. So I'm going to take the advantage of that to walk around the world. And once I'm going to reach his position, he's going to write out the story that he made.
Sit down and listen up.
All right, so this is the story that he made. You see, it was pretty fast. The language model was running while I was walking around. If I press stop, he's going to read the story out loud. And so I can walk a little bit around the story, the lizard wizard, and he will still read it out. See the frame rate is smooth. If I go a little bit too far away, he's going to be annoyed.
Hey, don't go far, Alice. I'm not done yet.
Closer, and he'll continue reading his story. Yeah, of course, I can always, if I don't like his story, I can just walk away and he'll ask us to start over.
I have to go now.
Okay, Alice. Go and do more things to inspire my next story.
All right, so he's not really annoyed that we don't like his story. He just asked us to do it again. All right, so that was a story. I hope you liked it. It's a pretty cute story. The main takeaway is you can see that the frame rate was really smooth all along the demo. And yeah, the computation was happening back in the background and not interacting with the game. So how did we manage to do this demo? So the first part was getting an AI model. So in our cases, we had 2 model criteria. First, it needed to be the smallest memory footprint. And second of all, the out-of-the-box performance needed to be very good. So for us, that's left us 2 models. One for the language model that was tiny stories. That was a really small model, around 500 megabytes, so not a big deal. And the text-to-speech was a model called JET. And again, it was really small, around 140 megabytes. So it was a really no-brainer for our use case. So now when we have the model, we tested it out. In this case, those 2 models are on Hugging Face, so you can download them and get started with the projects. So you have the models, you have it in your Unity projects, you play around with it, you test it out, you try to profile the performance. And the first thing to do is see if there's some obvious performance issues and how can you go ahead and improve it. So let's start with the tiny stories language model. So the first thing was, you can see on the right, the model has a lot of layers one after the other, and those layers are all expanded out. But if you look a little deeper, you realize that these layers are actually a single activation that performs all those operations. So if you could fuse those operators into a single kernel call, you would save a lot of memory bandwidth, a lot of read and writes, and you would have 1 dispatch instead of 5. So we already do this for a few node operators, but in this case, this activation called GLU wasn't fused. So we went ahead and fused that. We also can fuse instant normalization. Again, it's a more complicated subset of layers that are expanded out, but if you collapse them into a more efficient implementation, the whole model was faster. So we did those two optimization, and we ended up with a 10% performance win. So for the next optimization step that we did, requires you to kind of understand how the outputs of your model are being used. So in a lot of cases, you just execute the model. It's a black box. You don't think about it. You get the output, then you use it how you want. But in this case, it was really important for us to figure out how the output was used to optimize the model inference. So as you can see here, the last layer of the language model outputs a probability map for every single tokens in the dictionary for all the prompt size. So that's a humongous matrix multiplication that we're doing. We're doing that matrix multiplication for the whole input. But in our case, we just care about the last token, right? We're just generating one token, getting that token, and injecting it back into the input. So why do we need to do the work to recompute the probability for every single of our inputs? Well, the answer is we don't. In our case, we added a slice and we got the last token and then injected it back. So we don't need to do that whole math. So what we did is we inserted the slice before the map pool. And now all of a sudden, instead of doing a humongous matrix multiplication, we're doing an efficient vector matrix multiplication, and that's much faster. In our use case, in our profiling, that gave us a 50% performance win. All right, so now let's jump into the text-to-speech model. So this one is a little bit trickier, but it's also very important. So if you've programmed graphics in your game, you know that you do not want to interrupt the GPU. You cannot do a GPU readback in the middle of a frame. If you do that, the game will stop, it will have a frame hitch, and the performance will suffer. So it's really important to keep everything on the same pipe. So for this model, there was this layer, it was doing a reduction and then using the size, the value of that reduction on the CPU to compute a new tensor shape. So that caused a harsh download from the GPU to CPU, causing a lot of performance hit. So what we did actually is you can actually split the model in two, run the first half. Once that is done, you do an asynchronous readback on the output. You don't interrupt the GPU, you just tell Unity, give me the result once the GPU is done. You don't interrupt the rendering. And the next frame, you get the value and you give it to the next part of the model. You run that and get the output. That way you have no interruption, no download. You have a download, but it's asynchronous, but you have no interruption. And that yields a 50% performance win. All right, so we did those two optimization, but we're still not quite happy with the performance win. And now we go to a very common, it's not a hack, but it's a very common technique using game dev, is to know what is the frequency of your work. Do you need the result exactly the next frame? Are you okay with having some latency? Can I get the result in 5 frames, 4 seconds, etc.? For animation, is very used, like for faraway NPC, the animation will be a lower frequency. So for model inference, you can actually do the same thing. So for the language model, do I need the answer right away? Well, no, I can maybe wait a few seconds to get the result. In a lot of games, right, when you've done with your quest, you need to go back to the NPC to get the result of the request. So that's really an accepted gameplay trope, right? But in our case, we can actually do the computation while the player is going to the NPC. As long as the frame rate is stable and above 30, the player will not notice. So that's what we do. We split the inference over 2 seconds. We let the player come back to the story wizard. And while the player is coming back, the inference is happening behind the scene. So that's what we do. We call it time slicing. And what we do is we compute part of the model every frame. So for example, we slice the model over 60 frames, so around 2 seconds. And in the first 15 frames, we compute 1/4 of the model. The next 30 frames, we compute the next half, etc., and so on. And resulting after 2 seconds, we have the full model output. So for text-to-speech, we can take it even one step further. So in this case, if you tell a sentence like "tell me a joke" and like "why did the chicken cross the road," that's actually 2 sentences, right? And saying the first sentence takes some time, right? "Tell me a joke." That takes like half a second, but that's a lot of frames, right? We could actually do some computation while Unity is speaking this sentence, right? We could actually do some computation behind the scene while the first sentence is being taught and compute the next sentence. So that's like exactly what we do. We start the audio. While the audio is saying, we do the computation for the next sentence behind the scene. And once that is done, we play the next sentence and go on and so forth and so forth. Of course, we combine that with the time slicing and slice the model over many frames while the audio is playing. Overall, that is really a really nice technique, and that allows us to run those 2 models at really efficient frame rate on really low-end device. All right, so the question you might ask is, does this work on mobile? And the answer is almost. So the problem is the model is, we can get the performance to be efficient, but the model quality isn't there yet. Or if we use a more fancier model, which has better audio generation, the performance isn't quite there yet. So maybe in a few months, when we have a more efficient architecture or more optimization, it'll work efficiently on higher end mobile phones. So even though those models were not very heavy, it's around 500 megabytes, so that's like a big texture, you could try quantizing the model to save on disk space. So in this case, it's an example of how quantizing actually works for the language model. So you can see here we're quantizing the model in FP16 and in 8, respectively, and comparing the output prompts. So you can see it's very hard to judge if the prompt makes sense or not. You know, they're different, right? But are they good? Are they bad? For our use case, it was all of them seems reasonable. So again, you could try it out and see if it works for your use case. And so far as performance, the model size is around 500 megabytes, as I mentioned. Then performance is harder to measure, right? But what we do is we slice the inference over 2 seconds, and the frame rate is 30 FPS all during inference. So it's really not an issue. All right, thanks a lot, folks. I really hope you enjoyed. That's a wrap. Let's close the presentation with a few ending comments. So you can actually get started with Sentis today. It's open and free for all Unity users. You can scan the QR code there and download the project. You can also fill out a form on the website to schedule some jam session with us if you have any cool ideas you'd want to work on with us. So we have a pre-release version that is out now. It's the version 1.4.0. And Sentis will be coming out in production, coming out for Unity 6. So look around for that for around the end of 2024. So that's a wrap. Thanks a lot, everybody. Thanks for coming, and see you around.